Hi all, welcome to the lecture of Electronic Spectra of Polyatomic Molecules. Two early empirical laws govern the absorbance of light by molecules which are conveniently used as the combined Beer-Lambert's law. It states that the quantity of light absorbed by a substance is directly proportional to the concentration of the substance and the path length of the sample. Now, let I0 be the intensity of the incident radiation and I be that of transmitted radiation. If I is less than I0, then the sample has absorbed some of the light. A simple bit of mathematics is then done to convert this into something known as absorbance of the sample A, which is defined via the intensity of I0, intensity of incident radiation I0, and the transmitted intensity I by the equation A, which is the absorbance equal to log I0 by I. By the Beer-Lambert's law, the absorbance is proportional to the concentration of the sample in moles per liter and the light path length in centimeter L, including a proportionality constant. A becomes epsilon Cl, where epsilon is called the molar activity coefficient, which is a measure of probability of electron transition, or it gives the intensity of an electronic transition. This formula is the common form of Beer-Lambert's law. Combining it with absorbance in form of intensity, we will get A equal to log I0 by I equal to epsilon Cl. This is the basic equation behind electronic spectroscopy. Next, we have to see what does the electronic spectrum look like. From the first lecture, you got that electronic spectroscopy involves absorption of UV visible radiation by a molecule, and for this reason, the alternative title UV visible spectra is also preferred for electronic spectroscopy. This diagram shows a simple UV visible absorption spectrum of 1,3-butadiene. It is plotted with absorbance along y-axis and wavelength along the x-axis. The wavelength at which maximum absorption occurs is called lambda max. Hence, lambda max here is the 217 nanometer, which is in the UV region as in between 200 to 800 nanometer UV visible region. 200 to 400 is the UV part. Hence, we can say that 1,3-butadiene is a colorless compound as it absorbs the UV radiation. Now we have to see what happens when an organic compound absorbs UV or visible light, and why the wavelength of light absorbed varies from compound to compound. We know an organic compound contains various sorts of molecular orbitals such as sigma bonding, pi bonding, non-bonding orbital, pi antibonding molecular orbital, and sigma antibonding molecular orbital. Here, the sigma and pi bonding orbital contains normal bonding pairs of electrons. The non-bonding orbital contains lone pairs of electrons, and the anti-bonding orbitals are normally empty. When light passes through the compound, energy from the light is used to promote an electron from a bonding to bonding or non-bonding orbital to an anti-bonding empty molecular orbitals. So, the possible electron jumps that can occur in molecular orbitals are, the first one will be sigma bonding to sigma anti-bonding. Next, sigma bonding to pi anti-bonding or pi star. Next, pi bonding to sigma anti-bonding, pi bonding to pi anti-bonding, non-bonding to sigma anti-bonding, and non-bonding to pi anti-bonding. Here, sigma bonding to sigma anti-bonding needs higher energy. This transition, as there is much energy, the more energy gap is in between sigma to anti-bonding, and it needs higher energy, and normally the N non-bonding to the pi anti-bonding, it has a small energy gap. You can see itself in the diagram, and it needs a less energy. So here a higher wavelength or lower frequency can be absorbed. As you are interested in UV visible spectrum, the more important jumps in UV visible spectrum are from the pi bonding orbital to pi anti-bonding orbital. That is, I am giving in a different color. This pi to pi star transition and the N non-bonding to pi star transition. An absorption spectrometer works in a range about 200 to about 800 nanometers. Bigger jumps need more energy and absorb light with a shorter wavelength. So, I said that most probably the sigma to sigma star or sigma to pi star, this transition needs higher energy so that it absorbs light with very shorter wavelength, most probably less than that of 200 nanometer. That is, the molecule must contain either pi bond or atom with non-bonding orbitals, that is atom compound containing oxygen, nitrogen, etc. lone pair containing atoms with lone pair of electrons. They can have non-bonding electrons, will give this UV visible spectrum. Next, we are moving to the concept of chromophore. The term chromophore is applied to the system which exhibits absorption of a characteristic nature in the UV visible region. That is, those groups which give absorption in the UV visible region can be called as chromophores. Thus, in azo dyes, the aryl conjugated azo group is a chromophore. In nitro compound, the yellow color is carried by NO2 group, it's a chromophore, etc. are examples of chromophores. Thus, a chromophore such as the CO group has pi electrons as a part of double bond. CO group contains double bonds and also pi bonds and also has lone pair on oxygen atom. This means it can absorb light of two different wavelengths. It can have pi to pi star transitions and N to pi star transitions. As the energy gap of N to pi star is lower, it absorbs light of longer wavelength only which lies in the UV visible range, that is in the 200. That I am giving here the pi to pi star absorption is at 180 nanometers. Normally the instrument do not pick this transition, but this transition can have an intensity of 10,000. But the non-bonding to pi star transition is in the UV visible range, but as it is a forbidden transition by rule, it is only having an intensity of 2000. It is the epsilon. The intensity of transition or probability of transition is given by the epsilon, which is 2000. In the prior slide, we have given a unit, liter per moles per centimeter, I think. That is not important. In the modern experiments, we are not giving any unit to the epsilon max or epsilon. Only the digit is giving to represent the intensity. Thus, this is the importance of chromophores. That is, the chromophores are the UV visible active groups. Next is anophthalmos. It is also a term for a group which can shift the absorption to longer wavelength. That is, it can affect the chromophore or affect the absorption of a chromophore to longer wavelength, but it is not a chromophore. It itself not acting as a chromophore, but it can change the absorption of a chromophore to a longer wavelength, or it can make the make a functional group in the functional group in UV visible active. Can make it a UV visible active one. The effect of oxochrome have some examples. Alkoxy, methoxy, ethoxy groups, amino groups, etc. are oxochrome. And the effect of the oxochrome is due to its ability to extend the conjugation of a chromophore by sharing of its non-bonding electrons. Now we can see what is the effect of conjugation or delocalization in the absorption maximum of UV visible spectrum. Here you can see the UV visible spectrum of ethylene and 1,3-butadiene. The two gives similar spectra. You can see from the spectrum itself. The only difference is that for ethene, the absorption is at 171, nearly 180, and for 1,3-butadiene, it is in the 270 nanometer range. Here, the difference is that the absorption is moved to longer and longer as the amount of conjugation or delocalization in the molecule increases. For 1,3,5-hexatriene in the case, it will be more higher. The wavelength of absorption will be more higher than the two. Why is this? In ethene, There is one pi bonding or molecular orbital and one pi anti-bonding molecular orbital by the overlapping of two p orbitals. While in 1,3-butadiene, the interaction of two double bonds, with this interaction with each other, the two double bonds interact with each other, produces a delocalized system of pi electrons over all four atoms, which is known as conjugation. These four atoms, this delocalization happens. Here, there is overlapping of four p orbitals to form four molecular orbitals, two pi bonding orbitals and two pi anti-bonding orbitals. And notice that here, in this case, the two electrons will be in the bonding, pi bonding. Here, the four free electrons, two in the first orbital and the next is in the second bonding orbital. You can notice that the gap between HOMO and LUMO, as I already said, the most probable transition is from highest occupied molecular orbital to the lowest unoccupied molecular orbital. In this case, the gap between HOMO and LUMO has fallen. So it takes less energy to excite an electron in 1,3-butadiene than with ethylene, and hence there is the wavelength of absorption increases or energy of absorption or frequency of absorption decreases. In the case of 1,3,5-hexatriene, you can see the 3 pi bonds and there is much higher delocalization or conjugation, and hence there is the HOMO-LUMO gap is furthermore decreased, and hence the lambda max is still higher. Hence, you have to remember some points that there should be less energy gap between the bonding and anti-bonding orbital as the amount of delocalization increases. The absorption needs less energy as the amount of delocalization increases, and the maximum absorption or lambda max is moving to shorter frequencies or longer wavelength. And this longer wavelength is important for us as our spectrum always recording the lambda max. As the delocalization increases, the wavelength lambda max is always increases. If we extend this conjugation to compounds with massive delocalization, the wavelength will be high enough to be in the visible region of the spectrum, and the compound will then be seen as colored. A good example of this is the orange plant pigment beta-carotene present in carrots. Beta-carotene has the delocalization on much greater scale with 11 carbon-carbon double bonds conjugated together. So, its HOMO-LUMO gap decreased further, and it needs a less energy for this HOMO-LUMO transition, and hence the spectrum would be appeared with higher lambda max, which will be in the visible region, and hence we know carrot has an orange red color due to the pigment beta-carotene, and it gives the orange color to the carrot. Thus, electronic spectroscopy in general can differentiate conjugated dienes from non-conjugated ones, conjugated dienes from trienes, alpha, beta unsaturated ketones from their beta gamma analogues, etc. Since the degree of conjugation may suffer in strain molecules, electronic spectroscopy may be used to study such strain by correlating the change in the spectrum. The position of absorption may also be influenced by substituents, and A particularly useful application has been the correlation of substituent shifts in conjugated dienes and carbonyl compounds. All these distinctions are achieved largely on the basis that the longer the conjugation, the longer the maximum wavelength in the absorption spectrum. By this, I am concluding the electronic spectra of polyatomic molecule. Thank you very much, dears.